Good morning and welcome to Astronomy 100. Today is September 20th. We are doing week 6. So let me move the screen to the other, to the other screen. So we are in week 6, and this week is very important because we are going to close the first section, the 1/3 basically of the class. And there are important, very, very important assignments coming down the road. I'm sure you received the message I sent this morning at 7 o'clock pertaining to the grades. Some of you have seen changes in your overall averages, and that is due to the fact that I just went by the policy, basically as stated in the syllabus, where the grades have been weighted based on their type. Which brings me to an important type that is coming next week, and that is midterm. So the midterm is heavily weighted, and it is of utmost importance, and we need to really prepare for it adequately. Okay, we need to prepare for it very, very seriously because this could impact the grade drastically. So if you were doing okay so far, we're doing good so far, and if for somehow basically relapse when it comes to midterms, is going to impact the grade big time. So we really have to take care of that. On the opposite side, if you were not too happy with the way that the assignments were progressing, this is your chance. This is it, okay? To pull the class and put it where it needs to be, okay? Right on top, and that is the midterm. So the midterms have tremendous weight, as you can see from the syllabus, and that is basically the headline of the day today. Okay, this is the main thing. So we have to focus on that. So without further introductions, let me share with you the screen so that we can see exactly what's going on. Share, and here it is. So, of course, we have the objectives of the week. We have the previous week review. This is stuff that is related to items that are of importance from previous week. And also we have the lab discussion again today that is going to be posted. And here there is a video that is going to be posted. So if you guys are not live, you're going to be looking at the video here, okay? After it's posted, hopefully this afternoon, just like normal, okay? We have the last 2 units that are part of this exam. And then we have something called the midterm review, okay? The midterm review is due on September 29th, and it's worth 120 points. Here is the deal with the review. You either get 120 points exactly, not a single basically point less, or you get a 0. So those are the only 2 grades you receive for the midterm review, that is, okay? The review. If you start it, regardless of what grade you receive in it, you're going to receive a mark of 120. If you take the review, you're going to get the full credit regardless of how actually you scored in it. So if I score 10 out of 120, you still get 120. If you score 110 out of 120, you still get 120, okay? The point in here is that this review is supposed to help you prepare for the exam, okay? It is graded, and that grade of the review is going toward your participation grade. So it is important that you take care of the review, and the deadline, as I was saying in here, is September 29th, okay? Next week, Wednesday. So you have a little over a week to make sure you do what this is thing. Now, the way to get a 0 in this review is simple. Don't do it. So it is not recommended not to do that, okay? So again, it's 120 points. It's a lot of points. And you can get them basically by just opening the review, answering a few questions, and going through the entire thing, hopefully seriously preparing for the exam, regardless of how serious in your preparation. If you open it and you start it, you're going to get the full mark for it. Here is the actual exam. It's hidden right now because it's going to be available next week. The exam, did I say available? No. This is, let me open the review just to make sure, okay, if I can see it. Okay. It's actually, yes, that's correct. That's correct. Everything is so far I said is correct. Okay, so let me go back home. Okay, let me re-emphasize the fact that it is going to be due September 29th. The midterm itself is due October 4th, but it is going to be available September 30th. On Thursday at 8 a.m. is going to be available for you guys to start it. So the actual midterm is available on Thursday. You will have Thursday to take it. If you cannot, you have Friday to take it. If you cannot, you have Saturday, the weekend. Let's say you're working to Thursday and Friday. So that means Saturday, you have to have taken the actual midterm, okay? If you cannot for some reason because of one thing or the other Saturday, you still have Sunday. Now, worst comes to worst. You have Monday, October 4th to submit your actual exam. So this is basically the plan for midterm one. Midterm one is out of 100 points. And this is, again, a closed book. There are instructions in there on how to take it. At this point, it's not available, but just I'm showing you this to see the connection with the review. Again, the review is due the 29th, and that is a day before when this one is opens, okay? The actual review has 120 questions. Each question is worth 1 point. And it's only to help you prepare for the exam. It is a required assignment. Regardless of what you score in it, you're going to get either 120 points or 0 points. The only way to get 0 points is not to do it. Okay? So those are basically what's going on. So the first item of the discussion today is do the review. Okay. Before the 29th for full credit. Okay. That is basically what the thing is. So that is the item in here. Makes sense to you guys? We're here?
Yes.
Okay, very good. So let me go back into the screen where I was. Okay. Okay. So this is a freebie basically, and it's very easy to get 120 points in this case. So I'm hoping that you guys take advantage of it. The actual exam covers up to unit 38, all the units we did up to this point, including these units that we're covering today. Okay. So that means while I'm doing the review, I have to make sure that I am knowledgeable about all of the content of these units. And if you have any questions, please let me know. We should have no difficulty with it. I know I'm jumping a little bit ahead to next week in here, talking about another kind of assignment that is due October 23rd. So we still have plenty of time for this one, but I just trying to mention the fact that this type of assignment, the retrograde motion of Mars, this is a project, okay? This is not a homework, this is not a quiz, this is not an exam, this is a project, which means that you follow the instructions and you take care of it, and it also has some weight in the overall grade of things. So it is an important assignment. So we're going to talk about this one next week, okay? And we're going to be talking about projects now from next week on. So this is going to be an ongoing topic in here. So unless you guys have any questions, we can jump into this week's objectives. So I'm going to open them. And again, the first item in here talks about the review, okay? So the review for midterm is open. There is no time limit. You can take as many attempts as you want. It is graded as participation regardless of your actual score. And if you attempt it, okay? So if you don't attempt it, you're going to get 0. Otherwise, you're going to receive full credit of 120 points. If you don't try it, you will receive a mark of 0. Hopefully, you guys take advantage of these things. Yeah. Okay. Units 37 and 38 are the topic of this week. And again, the concepts that are going to be covered in here deal with two main things, really. It's really the Earth itself as its mass and its structure, okay? Because the Earth serves as a good example for the solar system, and also its atmosphere, because there are a lot of things that we can learn from the Earth and compare it to other planets and bodies in the solar system. This part of astronomy is called, basically, it focuses only on the solar system. Since we know Earth and we're familiar with it, okay, and we studied it extensively because it is within our reach, then we think at least it serves as a model for the rest of the planets in of the solar system, especially those planets that are of similar type as the Earth, rocky planets, inner planets, okay? So it gives us an idea of how it's structured, of how the other planets are structured. From the vantage point from where we're sitting, again, we have access to it. We can put our probes, our tools, and basically try to listen to the Earth through whatever activities the Earth is going. One of the key activities that the Earth undergoes are actually the seismic activities, namely earthquakes. And earthquakes are a very, very powerful tool to listen basically to the heartbeat of the Earth, what's going on inside of it. There are two types of waves when it comes to earthquakes. And the two types, of course, are the P wave and the S wave, okay? P stands for pressure and S stands for shear waves. Waves come in two different main forms, again, in general. Let me pick up this link in here to see if I can demo this. There are the compressional waves, okay? These waves, I have a slinky in here, okay? So these waves that are related to the stretching and the compression of the slinky, they're called compressional waves. You can call them pressure waves, okay? Because in the case of the Earth or in the case of sound, it is actually the pressure between the different layers and structure of the medium that these waves propagate in. On the opposite side, there is actually another kind of waves, which are called transverse waves. And transverse waves are characterized by displacement perpendicular to the direction of propagation of the wave. So the wave, for example, in this case, is going through the slinky. From one end to the other end, starts from the bottom and goes to the top. So if I click a kink in here, this kink will travel along the body of the slinky. But this kink itself is actually along the body of the slinky in itself. So there is compression, elongation, compression, elongation, compression, elongation that travels in the same direction. So this is called a longitudinal wave. Sometimes it's referred to as compressional wave. As opposed to another kind of kink that I create, which is sideways, and that sideways will create a disturbance that is going perpendicular to the direction with which it's traveling. So that is actually called a transverse wave. So those are the two types of waves. Hence, the earthquakes also exhibit this kind of behavior. And they are a very, very powerful tool to understand what's going on in the Earth, because each type of wave has a different speed and reacts differently to the nature of the medium they encounter. Okay, compressional waves would travel through all media, okay, regardless of basically the composition, if you wish, of the medium. Whereas shear waves, they break on surfaces that are loosely connected, like on the water, for example, okay? If you have shearing and you try to displace an amount of water versus the other one, in this case, basically the wave itself stops from propagating, but because they are easily displaced. Okay, so this is why one of them carries the energy to another side, namely the P wave, whereas the other one gets reflected and bounced back when it reaches the separation between a liquid and a solid. Okay. Because of this, and if an earthquake happens, let's say, for example, right now here, where I am sitting, and you have a detector somewhere else, okay? First of all, depending on the difference in the, we're talking about the surface now, we're not talking about the structure. Depending on this, the how lag with the difference between the times when the first one arrives and the second one arrives, it can determine the location of the earthquake, where the disturbance really started from. Okay, number one. Now, again, the waves do not just propagate along the surface, but also they go around to the depth, they go down. So depending on how far the first one bounced back and the second one arrives, I can determine the depth of that medium. Because waves in general, when they encounter different kind of densities, they bend. This is true for diffraction. This phenomenon is called diffraction. Basically, what's going on is that if you look, for example, on the surface of the pond, for example, and if you look at the fish actually is not in the position that you think it is, because the light, as it goes in, it breaks a little because of the difference in density, different in media. Same thing is true also for seismic waves. Seismic waves also have this property. Okay, all waves do, as a matter of fact, even sound does. Because of that, then in this situation, what's going on is we can determine the density of the different media once we see that this wave broke down and this is how it came back, and the other one broke down and this is how far it came back. I can determine the thickness of the region where the break happened, and I can determine also the density. Once I know the density, I have an idea of what makes it. Let's say, for example, the density turned out to be about 7 kilogram or 8 kilogram per cubic meter. No, 8 kilogram per cubic centimeter. That's, what is it? 8 tons per cubic meter. Then I know in this case that what I'm dealing with is actually iron, because that's the density of iron. If I find a number that is slightly different than iron, or I can average a quantity of iron and nickel, then I can tell what is the composition, that this has iron and nickel in it, and so on and so forth. So I can determine if density is about 3 kilogram per cubic meter, then it's not iron anymore, because iron is at least 7, or if it has iron, it's negligible compared to silicates, compared to dirt, basically, okay? So this is, again, how we determine not just the thickness of how much deep the regions are, but also the structure, the inner structure, without going that far, because we cannot dig 6,000 kilometers inside the earth to find its structure. That is, we don't have the technology for it. It's impossible, I'd say, at this point, okay? So this is one of ways of basically studying the inner structure of the planet, okay? So this is one way of understanding what's going on. So it turns out the Earth is made up of several elements. Iron is one of them. It's inside the core. Nickel actually is another one inside the core of the Earth. Those two are metals, and they have very, very important properties. They are conductors. All metals are conductors. There is a loose definition of metal when it comes to astronomy. Okay, in astronomy, anything heavier than lithium is called a metal. But in chemistry and in physics, actually, metals have specific properties. For example, oxygen is not a metal when it comes to chemistry and physics and engineering. And iron is a metal when it comes to physics and chemistry. but both of them, when it comes to astronomy, at least for the intergalactic materials, for the molecules existing outside of in the space, they're called actually metals, but that's actually a loose definition because anything heavier than these three first elements, namely hydrogen, helium, and lithium, are considered to be metals. But again, what I'm trying to say in here is that the iron itself, that is in the core of the Earth, mainly, but there is actually a small amount of it on the mantle, is actually and also the nickel has very, very important properties. The two key properties that I want to mention here is its ability to conduct both heat and electricity, meaning it can have electrons that can move in it, and those electrons that can cause electricity. Those, because of the currents that are generated then because of the motion of the electrons, you can create magnetism. In addition to the fact that both of these metals are actually magnetic in nature regardless. So if you have a magnet like this one, it's magnetic. Why? Because it's mainly made out of iron, and iron is magnetic in this case. This is, yeah, iron. And I have actually another alloy in here made out of cadmium that is also magnetic. Pull it out of this in here. Okay. So again, these are the different properties. So the magnetism and electricity are connected to one another. So as a matter of fact, you cannot have magnetism without current. So even inside this magnets that I've been showing, you can, the currents that do exist, they're actually on an atomic scale, but they're still currents that cause magnetism. Okay, so those are key properties. Oxygen, silicon is basically sand. Okay, so the sand of the beach is mainly made out of silicon, and magnesium is another element. So there are all kinds of elements on inside the Earth, and this some of the things that you can actually go about. I mentioned the fact that the P wave and the S wave, namely the compressional and transverse waves, and I actually demoed it with the Slinky in here, are what enables us to study the structure of the Earth. Okay. Again, we're interested from the vantage point of astronomy. What's going on with other planets? Let's say, for example, Mars. Okay. Mars must have a core. As a matter of fact, we sent InSight in 2017, that's a lander that landed actually on Mars, to see the structure of Mars, to listen to Mars quakes. Okay, so the quakes on Mars quakes versus earthquakes. Okay, the point being in here is that we wanted to understand what's going on inside of it. Mars is a lot smaller than the Earth. Okay, so and it's spinning fast enough, just like the Earth. As a matter of fact, the day there is slightly longer than the day in here, a few minutes, about 24 hours, both of them. Okay. So the question in here is that why Mars does not have a magnetic field and the Earth does. Remember what I said about the fact that currents are the ones responsible for magnetic field? Well, the Earth turned out to have a magnetosphere, to have a very strong magnetic field. That's the next chapter. Okay. Okay. So the Earth has a very strong magnetic field, and that magnetic field plays a major role. Actually, I'm sorry, it's this chapter. Okay. So this units, they don't call them chapters. And that is because of the fact that you have iron and nickel inside, and the Earth is spinning, causing basically this motion, and the motion in the convection layer also causing this motion of these charges, and the charges are currents, and hence they have a magnetic field, where the North Pole is more or less sitting next to where the North is, and the South Pole is more or less to where the South is. So the North magnetic pole and the geographical pole, they're close from one another, not exactly on top of one another. Okay, so the point I'm trying to say in here is that what happened to Mars? Why Mars does not have a magnetosphere like Earth? Why Mars does not have a magnetic field like the Earth? Mars in the past must have had also an atmosphere, and there are all kinds of indications for it. But once it lost its magnetic field, then the blast from the sun, from the solar radiation, and also from the cosmic radiation stripped most of the atmosphere of the planet away. And basically, at that point, the water is evaporated and everything basically lost. So that's basically what happened to Mars. So the reason why we believe what happened in Mars is, and the structure is similar to the Earth, is because it was a smaller size. It ran out of fuel, basically, what caused its core to heat up, lost a lot of it. So it cooled down to the point that you don't have enough currents going on inside the core. Hence, if the current is weak or no current at all, you will have hardly any magnetic field whatsoever to protect the planet from the particles that hit it. And hence, basically, it lost its atmosphere. In addition to the fact that because it's smaller, it has a weak gravitational field. So force of attraction is very weak. So the atmosphere also is lost because of that fact. Now, what happened with Venus? Venus is almost the same size of the Earth, and it still must have a lot of materials that are in its core to keep its core warm and hot just as much as the Earth. So why we don't have a magnetic field there too? Well, the answer to that is another one. You don't have enough spin. Mars spins Venus spins extremely slow on its axis backward, but it's extremely slow. So the motion there is not enough to cause enough friction for the iron core that it must have, again, because of the analogy that we draw with the Earth, to cause currents, and hence there is no magnetic field. So you have to have two things. You have to have a core that is hot enough, and that core has to be moving enough with enough spin to have a magnetic field. If you compare Earth, for example, to Jupiter and Saturn, well, Jupiter and Saturn, they're spinning fast and they are hot inside, so they must have a magnetic field. As a matter of fact, their magnetic field is ridiculously high, extremely high compared to the Earth. So that is basically what we believe is going on. You see how the Earth now serves as a model to understand what's going on. If you look, for example, at Mercury, Mercury is a lot tinier than Mars, so it must have lost a lot of its heat. And as a matter of fact, if you look at its surface, you can tell that it did not have enough, basically, atmosphere. Or its atmosphere, if it had, it lost it quickly, faster than what Mars did. And hence its surface is basically has all of this marks from the early bombardments that it suffered. And you have all of those crater impacts on its surface, as opposed to Mars. So the whole picture fits beautifully. And there is no difference between between Mercury and the moon when it comes to this issue. So the picture fits beautifully, and the model really serves to understand what's going on. So our understanding of the Earth is critical in here. The core, the structure, and so on and so forth. And as a matter of fact, as I said before, we're taking it a step further, where we actually go to planets like, for example, Mercury, and try to see its inner structure, using the same techniques that we developed here on Earth. The only trouble with this whole situation is that the Marsquakes are extremely small at this point in number and extremely weak, and they are still serving a lot of purpose right now. InSight had a little bit of issue in the beginning in terms of anchoring its sensors inside the planet, but it's still collecting a lot of data that is valuable at this point. We're still analyzing the data, by the way. So this is really what's going on in terms of our understanding of the Earth and how it helps us in understanding what's going on in other planets. Now, the Earth has, it's not just the mantle, and then you have the core and the inner core, the outer core, and all of the different layers as we learn them from seismology. It is actually has an atmosphere, okay? And that too can serve as a model to understand what's going on with the other planets, okay? I mean, just to give a quick comparison, Mars has hardly any atmosphere whatsoever, okay? And it's mainly carbon dioxide and some other elements in there. And the same thing is true, as a matter of fact, with Venus. Venus has an atmosphere, but the atmosphere on Venus is much, much thicker than the atmosphere on the Earth. Okay. So again, this helps us understand what's going on and try to learn of what's going on in the other planets. In the graph I'm including in here, it gives me the different structures of the atmosphere. The two main layers are the troposphere and the stratosphere. Okay. This is basically where the planes most of the times, the long-range planes, I don't mean the small planes that fly between Los Angeles, for example, and even San Francisco, they don't go that high, okay? But I'm talking about the intercontinental, basically, ones, the ones that fly between Europe and the United States and so on and so forth. They fly this high, basically. The pressure there drops dramatically. The density of the air drops dramatically. So the air density, as you can clearly see in here, drops to fraction of a fraction of a fraction of a percent. When does the air end? There is really no point in the sky when the air ends, okay? So it extends forever, except the density, namely the amount of air per unit volume, drops just above the Himalayas by almost 90%. Drastic number, not 90%. 90% is slightly higher. I would say probably 60% or 70%, depending on the numbers, okay? Himalayas are here, by the way, okay? So this is slightly higher than that. We're talking about 10 kilometers or 11 kilometers above the surface sea, okay? So at that point, around 20 kilometers drops to by 90%, okay? It's 90% by 35 kilometers. 35 kilometers is not a lot in terms of distance, 20 miles above the sky. Okay. Think of how far you can go, 20 miles. You can actually bike 20 miles. There is no problem with it. You can drive easily 20 miles in 15, 20 minutes at most. By then, you run out of basically air because 99% of it is gone. Okay. So this gives you an idea of the different density of the air when you go up. Okay. In terms of structures, at this point in here, you have the ozone layer. And what is the ozone layer? It's made up mainly of oxygen, except it has a specific weird structure. It's not an O2 molecule, but an O3 molecule. Basically, there is a shared bond between the two molecules, two atoms of oxygen on one side with a third one, okay? This is a highly unstable, basically, structure. So it decays back to oxygen, the normal oxygen. But before it decays, if there is radiation coming from the sun, mainly ultraviolet radiation, this speed up the process and it decays. So what is this doing to our planet? Basically, it's protecting us from the UV radiation. Because in absorbing it and transforming back through other processes, well, we're good. We're to some extent basically shielded from the UV radiation. Just to give you an idea of the electromagnetic spectrum, or light, basically. There is a very narrow region that enables us to see. And that region is from the violet color, which is very, very energetic, down to the red color, which is less energetic, okay? So this is basically the region that our eyes are sensitive to. Evolution has basically led us to see in this range. And that happened to be the peak of radiation from the sun. So because apparently the sun is nearby, so we evolved in such a way to be sensitive to the light that is emitted by the sun. That is where the peak radiation coming from the sun. The sun actually emits below the red and higher than the violet. Anything higher than the violet is actually more energetic. It comes with a lot of energy in it, okay? Case in point, you have the UV radiation, which can cause, basically, can damage the skin and can cause cancers. And if too much exposure to it can kill actually all living organisms. It's used actually as a sanitizer in some places, okay? To kill basically whatever you brought with you. Then comes the X-ray, and the X-ray are far more energetic than the UV. Okay? The X-rays are actually stopped even higher. The gamma rays, they're for the most part, They are actually more energetic than the X-ray, and they can cause far worse than that in terms of their amount. And again, because of this atmosphere, we are protected from them. As a matter of fact, there are particles that are emitted by the sun, namely electrons and protons. And those electrons and protons, they're emitted with tremendous speeds. And if they penetrate the atmosphere and come down, they can cause more damage than any of that. And there is also the alpha particles. The alpha particles are hydrogen, they're helium ions. And those helium ions, they come with extreme high energy with them, and they too can cause a lot of damage. But because they are charged particles, they have charges with them. And because of the presence of the magnetic field, they get deflected into the North Pole or the South Pole, causing what is known as the auroras. Okay? So once they go there, they interact with the atmosphere, the upper layers of the atmosphere, about 130 to 100, probably 10 kilometers. That is when they get destroyed in their interactions with the atmosphere, the upper layers of the atmosphere. So the atmosphere plays an important role in addition to the magnetic field of the Earth, because it's really moving them in a specific direction. Otherwise, they will blast the atmosphere itself and start basically working on it to remove it. So that is really an important point in here when it comes to the structure, okay? Well, the ozone layer has an issue with it. And the ozone layer, the biggest issue that it has with it is the fact that we send all kinds of materials, namely the CFCs. Those are basically used for hairspray and all kinds of things that can cause the depletion of this zone. And if this zone is lost, well, the UV will penetrate straight through. And the UVs are dangerous, okay? They are very, very dangerous. So it is actually of importance for us to protect this layer as civilization. Now, one other issue that we're facing in terms of solar radiation, especially, okay, is that radiation, again, I mentioned that it comes in the high frequencies, and the high frequencies include the UV, the X-ray, and the gamma ray. And the low frequencies also, you have the infrared. You have the red and the infrared. And then you have below that the microwave. And then below that, you have the radio waves used for radio telecommunications, for AM and FM signals and all of that, and even for your cell phone and all of these things. So that is low frequency, less energy. But the problem with them is not that it's really just that simple, because here is the problem. We receive light from the sun, which is really, for the most part, all radiation with different intensities. The biggest portion that we receive is actually in the visible region. Because of the atmosphere, it blocks a lot, but a lot of it also still can go through, okay? That's what we see. I mean, if you go outside, you see things because of the radiation coming from the sun, reflecting through all kinds of different medium. We receive it, okay? Then what happened? The Earth absorbs it. Everybody actually on the surface of the Earth absorbs that one, the waters and the land, and then they heat up. Once they heat up, they re-emit it back in the form of infrared. The trouble with the infrared, the presence of CO2 especially, and H2O especially, namely carbon dioxide and water in the atmosphere, absorb that radiation, the infrared specifically. So they are opaque when it comes to this one, meaning they are not transparent. So the radiation comes in, goes through. That means the air is transparent for most of the radiation. When it bounces back in the form of infrared, it's blocked and reflected back. So now when it's reflected back, radiation, infrared, by the way, is mainly heat, like what the microwave does in your oven. So when it goes back, it's going to be absorbed again by the Earth. Once it's absorbed, it's re-emitted back by the Earth. And it's absorbed by, reflected back. So now we're still getting an influx of radiation from the sun, but that form of infrared, which is really the heat, that is trapped. And this causes the greenhouse effect. That's how the greenhouses actually work. So if you have a greenhouse made out of plastic or made out of glass, what it's doing actually is taking the radiation from the sun and keeping it inside that house. That's what happened actually in cars too. If you close the windows and you put the car outside in the sun and check the temperature inside and temperature outside, you will see the temperature inside the car is several degrees higher than that of the outside, because again, radiation is coming in the form of all kinds of radiation. And when it's emitted back, it's emitted in the infrared from the inside, from the body of the car and the seats and all. When it's that, the glass will reflect it back. So heat is coming in and radiation is coming in from different frequencies, but heat itself is trapped in the form of infrared. It cannot escape. So this is the greenhouse effect. It's a useful effect, actually. It helped the Earth to become green to begin with and to warm up the Earth in the beginning. So it's really useful effect. In terms of agriculture, it's a useful effect, but not too much of it. Too much of it will cause basically the planet to heat up, and that heating will probably be under, we cannot control it anymore. So, and if we cannot control it anymore, it will cause basically life-ending events, basically destroying the forest. When it destroys the forest, there will be no more oxygen basically being produced, and carbon dioxide, they're released more and more into the atmosphere, speeding up the process of heating. So, because it will feed out of itself. But it needs carbon dioxide to begin with to start the process. But it's going to produce its own carbon dioxide released from the different fires and the different basically heating that is causing the different organisms to lose their ability to produce this. And so there is more carbon dioxide going to the atmosphere, meaning that the process will become even worse and worse with time. So the greenhouse effect is a dangerous effect that could really be devastating to all life forms on the planet. Okay? This is, I think, what happened to planet Venus too. This is really a lesson from planet Venus. It must have had an atmosphere not too different from ours. It must have had actually a climate not too different from ours. It must have had actually oceans similar to our planet. It could even have potentially had life. At this point, we don't know, but it could have had it also up to a few 100 million years ago. But then for some reason, a process that started the process of releasing carbon dioxide into the atmosphere, either from an impact of a big meteor that triggered several volcanoes on the planet, and those volcanoes kept on delivering a lot of carbon dioxide into the atmosphere, meaning it trapped more and more heat. Now it's really hellish planet. It's the worst planet in terms of heating on the solar system. So we have a good example of this process going awry, and the planet Venus serves as that example. Okay. In terms of temperature, you can clearly see also. So this graph is a very useful graph in here. Okay. In terms of temperature, the temperature actually starts to decrease as you go higher and higher. Okay. That's where you feel a chill when you go on the plane sometimes, when you go very high in the atmosphere. And actually you feel also, if the cabin is not pressurized, you will really feel the pressure going down because of the low density of the air in there. And then when it comes to the ozone layer, because of the kinetic energy, it starts to increase again to about 0 degree Kelvin, and then it decreases further. We are in this case in the ionosphere, and the ionosphere is basically when the different impacts in here from the different particles will ionize the atoms, because we have few of them. You have less than 1% of them. Okay, the molecules become ionized. And this is the ionosphere region. The ionosphere region plays a major role in port. First of all, in terms of the aurora itself, okay? That's what interacts with the particles coming from the solar system, and also from the radiation sent from the Earth, especially certain frequencies, the ones in the long range that are used for telecommunications. Those, they bounce back. It's like a metal. This one serves like a metal, really, like a reflecting shield. And they are used for telecommunications. So you send a signal from town that is broadcasting in an AM frequency, or send a signal within that wavelength, and it's going to bounce off of the atmosphere and come back here. So if you have no secrets and you don't worry about your enemies basically catching your signal, you can do that. And of course, if you're worried about them, all you have to do is encrypt the signal, and that's it. Okay? So this is the ionosphere, and then you can go higher and higher. So this is in terms of the temperature. So the temperature starts to become faster. So what's going on with the temperature? Why is it so high in this case? It is not that it is, I mean, if you put thermometer in there, probably it's not, you have to be careful in here, because the particles are moving so fast at this point. That is what the temperature is. The temperature is the kinetic energy of how fast the particle of the Earth, the air are moving. Okay, so this is basically in a nutshell the different topics that are covered in this unit. We'll talk about the Coriolis force in this case, which is a force that you're accustomed to. If you watch, for example, the bathtub or the toilet, for example, the way it spins, and that is really due to the Coriolis force. The Coriolis force is a force related to rotation. It's actually an inertial force. Okay, it's not a real force that is due to interaction of two particles. It's kind of a pseudo force. Okay, not a real force in a sense, because forces, we understand them in terms of push and pull. But the force, when you're sitting in your car and all of a sudden the driver accelerates and you feel yourself basically being pulled backward, that is the force of inertia. Okay, your mass times the acceleration. That is really the inertia. Or if you're sitting in a car and you go on a curve one way or the other, what is called the centripetal force, that too is a pseudo force. It's not a real force. It's really a force of inertia. Same thing in this case is also an inertial force, also the Coriolis, but this is due to rotation, the spinning of the reference frame, which is in this case the planet. And this is caused weather. This causes all kinds of hurricanes and different phenomena on the Earth. And this too has an important role trying to understand what's going on the surface, for example, of the big giant, like for example, Jupiter and even Saturn and the other planets that have gas in them, because they're spinning fast. And you will see there are hurricanes forming in the lower part of their hemisphere, and the upper part of their hemisphere forming in different regions. And again, that is due to the Coriolis force on those planets. So again, the Earth with its structure, meaning the solid structure, or even with the gas structure, gives us an insight into the inner planets, or even the outer planets and what's going on in their surfaces and their interactions and things like that. So these are the two units for this week. And I hope that you guys will go in detail reading about them. And if you have any questions, you ask please about them. And the biggest deal this week, and I really want to leave that with you guys, is to do the review. That is actually part of the discussion item. Okay, so there is no specific question related to the content this week, but more so on the process. So we have to do the review, because if you don't do it, you're not going to get any points. End of the story. So you really need to do it. Once you do the review, you're going to get full marks. The reason why this is important, and I know some of you, at least some of you messaged me over the weekend, at least one person did, about the grade. That student saw a change in the grade, I mean, big time, that the grade has changed, the average grade has changed. And I replied and actually sent a message to all of you guys, is the fact that the grades now are reflective of the syllabus, because the syllabus has a weighted average based on the different types of assignments. So you expect to see that, which brings us to the most important thing in terms of assignments really in this class, and that is the midterm itself. The midterm is next week. It's going to be open on Thursday next week, not this Thursday. So we still have about 10 days to ready ourselves for it. That is the purpose of the review. And go through all of the units. So if you don't have the book, this is really important that you have to have the book and go through the review question by question. Make sure you understand them, make sure you know what they are, make sure you understand what the question is asking and the answer, and you have to be at ease with it. I know in the instructions it tells you that you need to spend between 2 to 4 hours. For some of you, probably you will spend half of that much time. Okay? But for some others, the 4 hours may be actually a little less, so you might need to consider spending more than the 4 hours. But on average, it's between 2 to 4 hours. That's how much time you need to spend on this review. And then the actual exam is going to have actually 50 questions. Okay, and the exam is going to be available Thursday next week. Okay, and hopefully you will go through it the first time when it's available. And don't delay your assignments, because that's when panic comes in, and that's where all kinds of problems start to happen. Emergencies start to come, whether in family that you need to deal with, related to work where you need to deal with, or related to basically technology related, like excuse me, problems with the internet or electricity or some other things, or computer not booting up or something. The sooner you start with it and overcome all of these problems, the better you're going to be, because then if these things happen at the beginning, you have time to correct them. But if you start them late and you put yourself basically in an awkward position, you may not be able to recover from those situations. So again, this is the topic of this week. Any questions for me? Everything sounds good. If you guys don't have any questions, I'm going to stop the recording now. And for those who are watching this one recorded, please send your questions as soon as possible. Do not leave them toward the end and then panic time and things like that. Thank you.